Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear student, Assalamu alaikum. My name is Dr. Muslim Khan, Assistant Professor, Department of Chemistry, KUST. Today, the topic of our discussion uh, is HPLC ICPMS Part 2, Hyphenated Technique, uh, in the course Mass Spectrometric and Thermal Method of Analysis, lecture number 25, course code CHEM453. So, till now, we have discussed that how ions are basically generated in ICP inductively coupled plasma. So, usually a quadrupole mass analyzer is used as a mass filter. This quadrupole mass analyzer separates ions based on a mass to charge ratio. So when these different ions are subjected into the quadrupole mass analyzer, having four rods connected to AC and DC voltage, uh, these are changing periodically changes their voltage. So sometimes these two are so they're changing is to AC and DC voltage. So when these ions are passing through these rods on the basis of mass to charge ratio, they are separated in this vacuum chamber, quadrupole rods, and further subjected into the detector. So typical measurement times per mass unit is 10 to 20 milliseconds. This is analyzing more than 40 elements and less than 1 second. So I'm entering, then from this, I'm entering into electron multiplier detectors. Mass separation is also done in a magnetic sector mass analyzer. Not only quadrupole is used, but magnetic small mass analyzer. So magnet works also as a mass filter. So allows high resolutions. We have already discussed this magnetic sector mass analyzer in details in a mass spectrometry. So we won't go into the details of principle of magnetic sector mass analyzer. Basically, this is a magnet which is having a pole, and when ions are subjected into the mass analyzer, then ions with a bigger mass is um, going with the means different radius than a with a small mass. So on the basis of this, ions are then separated basically. So, discussing the ICPMS, what do we measure, what we want to know basically. This is a very basic look at the process because, like here, example of argon, potassium, and calcium. So, because most elements occur in more than one form isotope. You know isotopes and isobar. Isotopes are atoms of the same element having same atomic number, but different mass number is called isotope. While isobar is the opposite of isotopes, basically. So in fact, chromium has four naturally occurring isotopes. Similarly, uh, mm, hydrogen have three isotopes, potassium having three isotopes. This chromium exists in four different forms, all with the same atomic number of 24, but with different atomic mass. To make this a little easier to understand, let us a closer look in elements such as copper, which only has two isotopes, potassium having three isotopes. So the number of protons, number of electrons are the same because atomic number, but number of neutrons are basically different. So this is on the then it means that isotopes, different isotopes, because on the basis of mass to charge ratio will appear in different places in a spectrum. That what we measure. So this is the this is the uh, means SCPMS spectrum of a low resolutions. You can see here the intensity and the mass in AMU. So you can see that with the low resolutions, this is of manganese, this is of nickel, and this is nickel, isotopes of nickel. This one appearing at a different place because of 60 and because of 58 here. So similarly, copper. So this is copper 63, and this shows the natural abundance intensity of the copper. This is having bromine. Bromine is having 79 in 81. So one is 79 in 81. But because of the low resolution, that will be quite difficult to separate these two isotopes from each other in ICPMS spectrum. So interferences are basically those affect what you want to measure your analyte. For example, you are measuring calcium. Calcium is having atomic mass 40. So if anything, if any other thing having atomic mass 40, like argon, so that will interfere. Interfere means you don't know whether this signal is due to the calcium, whether this signal is due to the argon. These two elements are different elements, but having same atomic, but having same mass number. So this is known as isobaric interference. This to correct this, so you have to measure calcium 44. It means that different isotopes having a positive property means if calcium don't have a isotope of 44, then it was very difficult to correct this interference, whether this signal is due to argon, because argon gas is used in the ICPMS, inductively coupled plasma amines. So similarly, when you are measuring lead or mercury, so lead is having a mass number 204 and mercury is 204, one of the isotope. So this is also known as isobaric interference. Similarly, polyatomic interference, oxides or quarks. For example, you are measuring iron having atomic mass 56. Similarly, oxygen is there. So argon is used as a gas. So this become these polyatoms become, this is polyatomic, 16 plus 40, 56. This is 56. So then it is very difficult to know that whether this interference is due to the iron or this is due to the argon oxide. So instead of measuring then 56, what we for iron, we are not measuring 56 then, because it is very difficult to differentiate between iron signal and argon oxide. Then we measure isotope of iron having mass number 57, only to 2.2%. So the problem is then again is this isotopes of iron is present in a very low amount. Similarly, while I was working in on arsenic in my PhD project, arsenic is a monoisotopic. Arsenic is having only one isotope. Similarly, fluorine is also having a one isotope. So arsenic is having one isotope of 75. And then, uh, mm, so chlorine is everywhere, means this might be in your matrix somewhere. Then this argon 40 plus chlorine 35, we are making what? We are making 40 plus 35, 75. Arsenic is 75. Then it is very difficult to differentiate between argon chloride and arsenic. Then for measuring arsenic, what we want to do, we want to know about chlorine is also having another isotope, that is chlorine 37. We measure 37 plus 40, 77. We measure 77 signal. Then we minus that 77 from 75 if it is present. So again, similarly, sodium plus 40, 70, 63. Copper is also 63. It is interfering. This is polyatomic interfering. Then we measure 65 copper. but then again, 65 is because of the titanium and oxygen. You have to be careful here. Again, this one, so for this interference. Also, some of the time, doubly charged ions like this one, zirconium is 90 plus. So 90 plus M is 90, but here doubly charged divide by 2, not 1, because mass to charge ratio, then it is 45. So secondium is 45. These two interfere with each other. Similarly, nitrogen in the positive form, 14, but doubly positive. So 14 divided by 2 is 7, and lithium 7. These two interfere with each other. And also matrix dependent sometime. Uh, Although means in comparison to other analytical technique, uh, ICPMS is free of matrix uh, dependency, but still in some time it depends on metrics, which type of metrics. Some of the metrics are extremely extremely causing interference, so you have to be careful. So most elements have relatively interference-free isotopes, but they might be low in abundance. That's why it is sometimes it is difficult to measure them. So, for example, this is the example of a low resolution and high resolution mass spectrometer. For example, iron. Iron is having atomic mass of 56, in our argon oxide 56, 40 plus 16, 40. Then look, up till here, this signal is due to the iron, and this is the whole signal. This is due to this is the whole. Then some of the signal is due to the iron, some is argon chloride. But then there is a this is a misleading information to the scientific society, then, because you are reporting it, okay, that I have this sample, for example, this 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 soil sample is having this ppm of iron present in it, but actually in that your that report also argon oxide is also present. So it means that, but you then this is a quadrupole mass analyzer. This is element for example, with a high resolution, then you are you can, like, iron is 50, iron is 55.92, while this is 55.95. If your element, if your mass analyzer can differentiate up to this level, then iron is having a different signal, 55.92, and this is 55.9. But in a low resolution, we say 56 because of the low resolutions. Also, because of the dry and wet plasma. For example, this is when the plasma is wet, and this one when the plasma is dry. Again, for the same example, the element has the option of desalvator called Erudus. It is a spray chamber at high temperature, it's 110 degrees centigrade, and has membrane to separate water molecule from the sample. Reduces oxide more than 10 times, increases sensitivity 5 to 10 5 to 10 times. Drawbacks: it increase the memory effect, more difficult to tune, unreliable for volatile elements like and arsenic and silicon, etc. Otherwise, this is very useful. So blink subtraction, even pure water gives a signal, so we need to correct raw data. This is most significant for element whose atomic number is less than 82. Mostly result from molecular species from organ gas and sample solution. For example, argon oxide, as we mentioned it, with iron, and argon hydrogen 41, or this one, and carbon with CO and CO2, etc. Match blink with sample matrix, sample without sample. Samples dissolved in a 2% nitric acid, then we use 2% nitric acid. Seawater, distilled water with 3.5% sodium chloride, and then dilute. So sequential extraction, the various extraction agents like this, magnesium chloride, etc. So also correct from small contribution from material deposited in sample introduction system, tubing, spray chamber, torch, and cones. So once you have measured whether the elemental composition of your sample, so when you want to do the quantification, so it needs the correction for signal drift is needed and signal suppression because of the sample matrix. This so you are we are using internal standardization. We will discuss what is internal standardization. Also, during the quantification, we are doing blank correction. We will also discuss what is blank correction and calculation of element concentration. External standardization is also uh, used during that one. Also, um, isobaric interference for isobaric interference overlap corrections and also data quality check reference standard and duplicates, triplicates, etc. So signal drift. This is a this is a linear drift is a function of time, and this is curve linear drift is a function of time, and this is curve linear drift is a function of mass and time. This is done. One solution is to run standard often, but this time consuming. And what if you have many standard for many different elements? So many standard. Yeah. So this is the assumption is that all elements behave similarly to and 1 plus comma period. Also correct for signal separation due to matrix effect. So common internal standard is indium, this one. Internal standards are basically added like this is a standard, this is your sample. To every sample, standards are basically like standard 1, standard 2, standard 3, and 4, and the samples, this one, similarly this one. So this is indium and drift. This how much how much drift is occurring. So this is known as internal standardization. We are actually measuring this. And external standardization, we mostly use multi-element standard nitric acid solution that contain 10 to 20 elements. Typical precision is around 5% standard. We have discussed this external standardization, how this calibration curve is achieved. This is reached to the blank level limit of detection also. Standard addition method, one of the useful method for the sample with a strong or unknown matrix. So what we do, this sample, volume of sample and concentration of sample, a spike with a known concentration is added to the sample. So precision similar to external solution, but more accurate. The drawback is that approximate concentration needs to be known. It is very labor intensive. So we also spike. Then when this calibration curve is reached here, then it is on the negative side of this one. We measure the concentration of the sample here by this standard addition method. Also the isotopic dilution method, addition of enriched isotope spike to the sample. This is this yellow is natural, and this one is spike 1 and spike 2. For ultimate precision and accuracy, better than one for no internal standard necessary. The drawback is that approximate concentration need to be known. Does not work for monoisotopic element, labor intensive, and spike often expensive. Like this is 26 PB, 27 PB, and 208 PB. So this is isotopic dilution, and we have also discussed this one. So I don't want to in detail this isotopic dilution method. So elements are isotopic ratio. When you want to know the ratio of element relative to one other element, magnesium, calcium, strontium, calcium, other element and forms. So when you want to do isotopic ratio, lead isotopes of 207, 206, lead 208, 206. This is a very high precision is needed and preferably with standard composition close to the sample, standard and sample with similar concentration. The ratio of element isotope served in internal standard does not need to be added. This method is also used in the quantification. Uh, Coming to the detection limit. Limit of detection, the lowest concentration your instrument can measure is called the limit of detection. How it is calculated? So we measure the signals of the blank, the 10 blank, and this 3 and 2 standard deviation of the 10 blanks, and measure blanks of 6 to 10 times during a run, and calculate standard deviation, and limit of detection is this one. So limit of quantification is 10 and 9 and 2 standard deviation of the 10 blanks is the limit of quantification. So here is the periodic table. So ICPMS detection limit. Here it is given as means those element are showing with this like with no color. That is means this can't be measured with the ICPMS. With this color, this is less than 100 ppt parts per trillion, like these elements. And with this yellow one, this one is less than 10 ppt, the yellow one, and this one is less than 1 ppt, while the green one is less than zero point 0.1 ppt, and while this one is less than zero point zero 0.01 ppt. So overall you can see that how lower limit of detection can be achieved with the ICPMS. It means that ICPMS is limit of detection is not comparable even to the other techniques. Means even you can go to the very low level of element detections. Reference standard plus blank metrics often usually different metrics are more complex than calibration standards, so unexpected, and you are getting very unexpected interferences. So measure something with known composition and similar metrics is reference standard. Sample digestion procedure involve many steps of adding acids, drying, etc. Each will introduce some contamination. Measure something without sample that has gone through a whole dissolution procedure. Digestion blank is basically needed. So once you perform your experiment, then you are processing the data, which is very the important part of your experiment. Show a Excel sheet, normalize to internal standard, check for outlier which may indicate spiking errors, and calculate the calibration line uh, from normalized intensity and standard in concentration, and then calculate concentration of calibration blank plus standards and check if okay, and then calculate concentration of sample including digestion blanks, including dilution factor, and subtract digestion blanks from your sample and correct for isobaric or lapic interference if measured. Evaluate precision and accuracy with duplicate and reference standard. These are the steps which are usually followed while processing the data. So you have to be careful while means needing analytical accuracy and precision. You know that what is precision and what is accuracy. The agreement of the different the agreement of the closeness of the data point with each other is known as precision, while the closeness between the average of your duplicate, triplicate, or even pentate with your actual value is known as accuracy. But as an analytical chemist, you both have means, and this is the reference value. How close is this average value to the reference value is known as accuracy, and how close these with each other, these different points, is known as precision. But as an analytical chemist, you must have both accuracy and precision, both very good. So internal precision on a sample during analysis, external precision on a several digestion of the sample. Accuracy is the result of a reference standard with your value. So this RSD versus RSE improves with the number of repeats. So RSD doesn't. So significant and should reflect precisions like 0.30, so point is up to this one, relative standard deviation. So when you are starting your experiment, you have to tune the instrument. How? So you have to check the torch position if cones having been cleaned, and whether or not. So you have to clean the cones and very in a nice way and very accurately. Similarly, you have to optimize the nebulizer gas flow, most important variable in wet plasma. So on a quadrupole, depend on autosampler that is used zero point 0.9 to 1.1 liter per minute. A gas nebulizer gas flow is used. An element varies little, 1.05 to 1.1 liter per minute. So aridus gas flows if used element only, argon this one and nitrogen is this one. And then check intensity of your internal standard, this indium 105. This must be more than 20,000 an element. This one must be like this for a bit one. Check oxide interference, the cerium oxide, cerium less than 3% in wet plasma, less than 0.5% on aridus and only element only. Check doubly charged ion for barium, this one, less than 3% in wet plasma. So these are the protocol used for instrument tuning while performing experiment with HPLC ICPMS. Optimizing the nebulizer gas flow called plasma gas an element, you have to optimize the nebulizer gas flows, and this is how look like this is indium 115, cerium 14, this one, and the green one is cerium oxide, and this one. So you have to optimize the nebulizer gas flow as well. So coming to the methods and sequence batch, software on a quad and elements are different, but principles are the same. First of all, when you are starting your experiment with HPLC ICPMS, make a method. Select isotope you want to know from a periodic table, which isotope you want to perform your experiment, and then decide how long you want to measure each isotopes. This is very important. And then decide how many repeats you want to do. Triplicate, quadrate, means pentate, and then you have to set up the sequence element or batch, which sample you want to first of all blank, and then standard one, and then standard two, standard three, and then your sample one, sample two. So you have to set up a sequence. Put all the blanks, standards, sample in a list and indicate their position in autosampler. This is very important. Define which method you want to use and indicate update and rinse time, and then start your experiment. This is how you are. Then lab work and cleanliness and safety. Keep a lab book, a record of sample handling. If something goes wrong, you can track back what you did, because you have to analyze yourself as well, that what I have done wrong during experiment. And work clean. Wear gloves when handling samples. Clean equipment, vials, pipettes, tips, etc. before use. Acid leach is best. Also, wear lab coat, full body in a clean labs, including hood, and keep open sample in fume hoods if possible, not to contaminate, or even some fumes are dangerous. So that's why keep open sample in fume hoods, and work safe. Very careful with a strong acid, especially hydrofluoric acid. Also, wear gloves and protective clothing. And when you perform your experiment, clean up after use. So these are the simple things you have to keep, because as an analytical chemist, when you want to work in a very accurate and precise way, so you have to clean all the things properly. Mm. And then lastly, going into the checklist, well, first of all, okay, I have prepared the sample, but how? Decide how to dissolve your sample, and then keep a lab book, means write the steps what you want have add to this your sample, how much you have add to the sample, and work clean and safe, include digestion blanks if possible, reference standard. And then sample analysis, book your time in advance, at least a week at least. Check with me. Check means uh, is a supervisor, check with me whether instrument is available or not. Prepare sample and standards for analysis, usually on the same day, just an hour before. Set up a sample run in ICPMS software. Tune an instrument, start run, clean up after use, data processing and evaluation, and then you have done your experiment. And then um, uh, coming to when you want to see these things, you have to see it in GD question analytical chemistry 7 edition, Scooge and West means fundamental of analytical chemistry 9 edition. And thank you very much for today lecture.